Okay, also then I will talk about potential impacts of ductwork and envelope leakage. So this presentation that I've prepared with Peter. Presentation will be divided into two parts. First part will be about ductwork leakage. We will see some good and bad examples, also some typical leakage rates, and potential implications. And then the second part, I will look at envelope leakage. I will give you background on how does it work, and also on possible airflow rate impacts. Let's start with ductwork leakage now. So we'll see that we can have very nice technical solutions for making duct systems. You can see some very good examples here on this slide. So not only they look nice, but also they are quite airtight. I mean, they were Class C or Class D ductwork, and also some interesting features in the slides, like for instance those clean openings that you can see on the bottom left picture. So you can see that there's a couple of openings to make sure that you can clean the system during the time of the system. So it looks very nice and free, I would say. But in fact, you can have also this kind of systems on this, and I would say this is much more typical, at least for France or for Belgium, where we had this project that Peter mentioned a couple of years ago that was funded within the SAVE program. We can see that obviously you look at, for instance, the bottom left picture here. Obviously, there's a big leak here, and probably a big fraction of the flow is going to leak out to the ceiling. And actually, in this case, it was a false thing, which was unconditioned. So basically, air that is going into the ceiling is, and in that case, it was a system that was used also for preheating the air. So, well, there's obviously a considerable amount of energy that is lost directly in the ceiling. So this sort of art piece on the right-hand side, which obviously is not optimal as far as pressure drops are concerned. Well, it's not very nice either, I guess. Peter mentioned also that there are leakage classes that are defined in the European standard. So the European standard is 12 to 37, and well, there are leakage classes that are called leakage class A, B, C, and D. So it might be a little bit confusing because leakage class D is actually tighter than class C, which is tighter than class B, which is tighter than class A. But all this, I mean, afterwards, it's not really well, basically, the systems are classified according to their leakage rate, so in liters per second, and also per meter square of duct surface area, and for given pressure. So basically, if you pressurize your system, well, you have data that look like the red points that you see on the figure now. Then that means that your system complies with leakage class C because they are all the points are below the limit of leakage class C. Peter showed this picture also, where you can see measurements that were done in France, Belgium, and Sweden. And of course, what is striking is that we had to make those additional classes. We had made those additional classes because we could not classify the systems according to the standard. So we had to make those classes that are 3 times class A, 9 times class A, etc., with the same logics as the one of the previous, in order to be able to show them on a single graph. And also what is striking is, of course, the difference with the situation in Sweden, where you see that a lot of systems are class B in the sample that we have chosen. And, well, we have a significant fraction also that are class C or even class B. So I wonder, why is it really a problem to have a leaky system? Well, let's look at two limiting cases. The first case would be the case where we have the fan flow which is not adjusted to compensate the leakage airflow rate. And in that case, well, you have you don't have really an energy penalty because you don't compensate for the leakage airflow rate. But on the other hand, you don't have the right airflows at the registers, so you may have some air quality issues. The limiting case is that the fan flow is actually adjusted to obtain the correct airflow at the registers, the airflow terminal devices. And of course, then you will have energy losses because you will increase the ventilation load, and also because you will have increased fan power demand. I think there's an issue here. Okay. So here I've taken a slide from an article which I just presented at the Builder Symposium in May in Berlin. So a few weeks ago. In this slide, what you see is that the efficiency of a heat recovery unit, it was a house. The test case was a house with a ventilation system with a heat recovery unit, and the normal efficiency of the heat recovery unit is 80%. And you can see that because of poor air tightness and also because of insulation issues, then it dropped to about 43% because of poor air tightness and poor insulation of the ductwork. So it's quite significant, and you may wonder why you would have such a heat recovery unit with one of the energy in the ductwork. And of course, you have also to consider that you have the issues such as increased fan energy use or increased ventilation load to consider. Okay, now let's move on to envelope leakage. So, well, it may be a good idea to look a little bit at the physics behind that. So here's a very simple example. We have a house with a balanced ventilation system. You have wind, which is blowing past the house. Then you will have an overpressure on the windward side of the building and an underpressure on the leeward side of the building. And you will have leakage airflow rates, which are represented by these arrows here. And this flow rate is going to increase the ventilation load of the building. That's the point. And also, well, that is going directly here through the building is not passed through the heat exchanger. So there's no way that you are going to recover heat from this air. Well, of course, one example on the balanced ventilation system. Well, you could have similar analysis for an extract only system or even on a natural ventilation system. Also, other issues, for instance, for the disturbance of airflow patterns, because, well, basically the leakage is completely uncontrolled, and you have, well, backs are looking in that you basically don't know. So you don't know the leakage distribution. You may have rooms that are that have a high leakage rate, and on the other hand, other rooms that are little leakage, and therefore it's going to disturb the flow pattern, as you can see on this slide. So the aim, of course, is to build height, but at the time to ventilate correctly, because of course if you only build height and you don't have a proper ventilation system, then it's of course a problem. Now on the way you characterize the leakage flow rate or leakage. Well, this is one indicator, the N50. There are several other ones that you can use in this, but well, this one happens to be handy for the rest of my presentation. So, the N50 is basically the airflow rate at 50 pascal. So the airflow rate at 50 pascal when you pressurize the building divided by the heated volume. So that you pressurize the building by sealing all voluntary openings, and then all the flow that is to pressurize the building actually is a leakage airflow rate. So that's not verified, but there may be some issues actually to measure this, but it's possible in any case. What is interesting is to know what is the actual infiltration rate. Well, actually, it's complicated because the infiltration rates also depends on the climate and the wind and things like that. So it's quite complicated. But there's a rule of thumb which is very convenient that says that the infiltration rate is roughly between N50 divided by 30 and N50 divided by 10. So it's possible, I would say, as a rough estimate, to take 50 divided by 20 as an indicator for the filtration rate. So here in this table, what I've done is that I've the infiltration airflow rate base rule here, and it to reasonable air change rates. So reasonable air change rates, I would say, in Europe are between 0.5 and 0.8 air changes per hour. And you can see that the infiltration airflow rate typically is between 20 and 30%. So in that case, I have assumed that the airtightness was air changes per hour at 50 pascals. This actually may be a little bit optimistic. Look at this data that was collected by Ioan in France. You can see here for residences, for instance, more than 40% of the buildings that have an air leakage rate which is higher than air changes per hour at 50 pascals. If you look at the buildings, it's even worse. If you look at industries, but I mean the sample is smaller. It's only 20 or 25 buildings, whereas for residences it was 215 buildings. This is the reason why there's been a large project that has been initiated in France, initiated by Cité de Lyon, to help actually designers and workers both on methodology and also on technical solutions. So here are some drawings that I have extracted from a handbook that was just published by Cité de Lyon through this project. Basically, these drawings are very nicely done to help designers and workers understand how you can actually make an airtight building. This is one slide of the handbook where you can see that it goes also very much into the details of the execution, because it tells you what kind of system you can use in order to build airtight at this connection, for instance, and also who is involved when actually installing this system. Conclusions now. Well, of course, the significance of envelope and ductwork leakage on energy use and ventilation system efficiency has been debated in the past. There are many things that have been have been done a couple of years ago. Well, potential impact a specific attention in the context of nearly zero energy buildings. It is clear that when you lose you don't control 1/3 of the airflow rate that building, then it's very complicated to make a nearly zero energy building, if not impossible in many cases. There's obviously room for improvement. Well, probably I would say in most countries outside of Scandinavia for ductwork systems, and we would say probably for all countries as far as envelope airtightness. And also, well, obviously the range of technical solutions that are available to overcome these problems will exist. There's technical solutions, but also methods. I just showed them. But obviously they are not widely used. So, well, the good news is that they exist, and what we should try to do is to make that happen on the field and make sure that these are really applied in the field. So with this, I would like to thank you for your attention. Well, maybe we can take a few questions before we move on to the presentations.